Picture a high-energy waveform propagating through a complete vacuum. In communication theory, we must define this concept formally. A signal is any arbitrary function of time, and its value at any given instant can be either real or complex. But a physical signal rarely exists in isolation. It enters a system, which is mathematically defined as a strict set of rules mapping an input time function to an output time function. Modern communication networks are built entirely from these interactions. They are sequences of interconnected functional blocks, where a specific input signal is fed into a system to produce a newly processed output. Because the system actively alters the input, we cannot calculate the exact output without first isolating and mapping the precise mathematical properties of the raw signal itself. To analyze any transmission accurately, we first have to build a rigorous mathematical taxonomy that classifies every possible physical waveform. To categorize these waveforms without ambiguity, we analyze them along two completely independent axes, time on the horizontal and amplitude on the vertical. The terms continuous and discrete refer strictly to the horizontal axes. They dictate solely how time is measured. Conversely, the terms analog and digital apply exclusively to the vertical axes. They define the behavior and precision of the signal's amplitude. The left chart shows an analog continuous time signal. The unbroken curve maps continuous time to infinite amplitude values. The right graph displays an analog discrete time signal. We measure at strict time intervals, but the arrows point to infinite analog y-axis values. Taking discrete time samples does not inherently digitize the value. The amplitude can remain entirely analog even if the timing is chopped into distinct segments. This graph illustrates a digital continuous time signal. Here, time flows without interruption, but the amplitude is sharply quantized. It snaps between rigid binary states, creating harsh right angles. Finally, this chart shows a true digital discrete time signal, which forms the baseline for modern computing. The data points are locked to specific intervals on the x-axis and forced onto strict quantized grid increments on the y-axis. Decoupling these axes lets engineers strictly separate the continuous sampling of time from amplitude quantization, ensuring mathematical precision when mapping analog to digital conversions. Beyond physical shape, signals are classified by predictability and their mathematical behavior over an infinite timeline. The top chart shows a deterministic signal. Its future values are dictated by an exact mathematical function, like this perfectly repeating cosine wave. The bottom graph represents a random signal. Its erratic spikes are unpredictable, requiring probability theory and stochastic models to analyze. Once predictability is established, we test the signal against its total energy limits, bounded between negative and positive infinity. We calculate this using the energy integral. We take the squared magnitude of the signal, g of t, and integrate it across infinite time. For a waveform to meet the absolute condition of an energy signal, this integral must evaluate to a finite number. If a continuous periodic signal repeats indefinitely, its energy integral diverges to infinity, a failure state. To solve this divergence, we use the power integral. Dividing the energy over a single period and taking the limit extracts a finite power value. Because these limits are mutually exclusive, every continuous signal must be strictly categorized as an energy signal, a power signal, or rarely neither. Now that the taxonomy of the input signal is defined, we establish the mathematical constraints of the processing block it enters. In communication design, we analyze networks primarily as linear time-invariant, or LTI, systems. An LTI system requires the superposition property. This means the system's response to a combined input is exactly equal to the mathematical sum of its responses to each input individually. It must also strictly enforce causality. By physical law, a system cannot produce an output sequence before an initial input is actually applied. Translated into rigid mathematics, this means a causal system's impulse response, h of t, must equal exactly 0 for all time before t equals 0. Engineers map the exact boundaries of these causal systems by probing with the Dirac delta function. The Dirac delta is not a traditional signal. It is a strict distribution, a generalized mathematical function designed to trigger an instantaneous impulse response. An LTI system becomes entirely predictable mathematically when its impulse response strictly obeys causality and superposition. With the signal classified and the LTI system mathematically locked, we combine them to calculate the final transmission output. This calculation is driven by time-domain convolution, which mathematically folds the categorized input signal into the system's precise impulse response. Convolution calculates the exact area of overlap between two waveforms as one slides continuously past the other along the time axis. But executing this sliding infinite integral for complex continuous signals forces an extreme computational burden on the processor. To bypass this processing bottleneck, communication engineers employ an exact mathematical shortcut. Convolution of two signals in the time domain is perfectly equivalent to simple algebraic multiplication in the frequency domain. Standardizing this entire taxonomy, bounding infinite signal limits, and enforcing rigid system linearity creates the uncompromising mathematical architecture required to execute advanced communication theory.